Thanks very much, Enrique, for the invitation. And I would like to tell you a journey that started a few years ago. I think around 2018, I started to work on this topic. So it's already 8 years, which is kind of unusual for my somehow my activity. Usually I have interest in an area for a small time, few years, and then I move on. But this topic remained with me because apparently it's way richer than I expected. It continues to offer interesting ideas, and I'll try to introduce you on the topic. It's a very good moment for me to tell the story because we have been thinking about it for a long time. So I start talking about optimization first of all. So there are many places where somehow non-convex optimization come into the game, and in particular, it doesn't work very well, sorry. In all the problems where non-linear models are involved with parameters that you want to optimize to fit the model to data. This can be called data assimilation in the classical inverse problem terminology, machine learning, or model parameter estimation. All of that brings immediately into non-convex optimization problems to be solved. We will see that machine learning is certainly one of the hypes where this non-convexity comes into the game when you want to train neural networks, for instance. But that's not necessarily the goal where somehow we want to apply this stuff, because there are very good, simpler somehow ideas that work apparently very efficiently, like stochastic gradient descent and variations on the theme. I'm going to talk about that as well. But we have other applications in mind, and I will talk about them later. So in general, you have an objective function, which is non-convex, and you want to optimize it over a certain domain. We will see that the domain can be a subset of a Euclidean space, but it could be also something more involved, like a manifold or something like a Lie group or things of the kind. So we know very well by somehow the latest developments in machine learning that classical methods like stochastic gradient descent, they are somehow effectively applied, and they are known to generically escape the trap of critical points. They are scalable, and this seems to somehow create a certain bias when you train with these methods towards interesting local minimizers. And certainly this is one place where somehow these methods are so successful. If you want to analyze what these methods do, you have to recognize, first of all, that they are discretization in time of certain stochastic differential equation, in particular the so-called overdamped Langevin dynamics. So if you look at this discrete time evolution, you recognize that is a Noyer-Maruyama discretization of this stochastic differential equation, meaning that at each time t, the stochastic variable xt has a certain distribution, and the law of that distribution that here we indicate with law, how is the pointer here? Yeah, the law is described by a certain partial differential equation that is having a drift term and a diffusion term. If you want to analyze how the law of the system go, you try to look at the large time behavior of the solution of this PDE. How this PDE is related to the stochastic differential equation, I will show it in a moment. What is interesting is the large time behavior. So we'll go back to that in a moment. First, I see how this PDE is actually obtained. The idea is that you take a test function, you test it on the stochastic process, you apply the Ito calculus, you consider it in the integral form, you apply expectations so that the law comes out in the game, and then you recognize that what you just wrote is the weak formulation of a certain PDE. That's how you connect somehow the SDE to the PDE describing the law of the system. At this point, it's good to introduce a certain distance, because the law is a probability density or a probability distribution or a probability measure. And in order to understand how you approach or estimate the distance between one measure to another, you may want to introduce some distance. The ones that we may want to take into consideration is the optimal transport distance, the Wasserstein distance of order 2, that is here described in the square form, that represent how you transport pieces of mass from one measure to the other one by minimizing the cost of the physical distance between the location. So now I mentioned that this is a gradient descent, meaning that we are optimizing a function going along the gradient, and it turns out that the PDE itself is a gradient descent with respect to a certain calculus and a certain somehow kind of functional analysis. And here the functional that we are interested in is the sum of the averaged objective function that you want to minimize and the term which is the negative relative Boltzmann entropy that or the Boltzmann entropy here with respect to the Lebesgue measure, and you have this functional that is a functional over the space of probability measures. And if you want to understand how to kind of consider variations of this functional, you have to remember that you are now on the space of probability measures. So if you want to move, in order to understand variations, you need to move in the space of probability measure. The way you move on the space of probability measure is by considering divergence equations that preserve mass. And so you give a certain direction of differentiation, and you move in the direction W, let's say. W is a field that represents a sort of direction when you want to differentiate, and you move from the given probability measure rho 0 by solving this PDE in time. Therefore, when you try to see the variations of the functional, you do it by evaluating the functional on the solution and by integrating in time somehow the variation. What it turns out is that you obtain a sort of Frechet differential in a certain sense. It's not really a Frechet differential because we are on a metric space, not on the classical somehow Euclidean setting. And you see that this object is applied to the direction where you want to go as it were a sort of Gateau differential. And this object can be explicitly written in a certain form. So this is the gradient of this functional with respect to this kind of differentiation. If you take the negative of this gradient and you plug it now inside this equation, you are actually going in the opposite gradient direction with respect to this functional. Okay? If you do so, what you obtain is exactly the PDE that you have seen before. So the PDE before turns out to have a gradient flow structure, and that's somehow the fact that you can connect gradient flows at the end, at the side of the function that you want to minimize, to gradient flow with respect to the probability measure. Now, the equilibrium state or the minimizer of the functional that we have seen before coincide. So the minimizer of this functional. At the same time, the steady state of this equation, it's a measure that has this form, and it is called the Gibbs measure. Okay? And depends on the parameter sigma that appear here and represent, in a certain sense, concentration. This measure, this density, is concentrated more and more around minimizers of the function E, where this value is maximal. And for sigma tending to 0, you can expect this to concentrate more and more on minimizers of the function E. The question is, when do you expect the large time behavior to converge there, and with which rate? Okay? This is a classical question that has been answered in the field of these Fokker-Planck equations, and in particular in optimal transport. And it comes with results back to the 80s, where two quantities have been introduced. One it is called the relative entropy, the other one is called the Fisher information. And in this case, somehow you consider an entropy with respect to a given probability measure. In particular, we consider a probability measure of Gibbs type. And if you do so, you say that this measure fulfills this log Sobolev inequality, that's how it is called. If for any other measure mu, you have the inequality fulfilled for a given constant lambda. It turns out that if the function E is a L infinity perturbation of a strictly convex function, then this inequality holds with lambda being related to the lower bound of the Hessian of the strictly convex component of the function and the L infinity norm of the perturbation. Why this is important? Because if you differentiate the entropy along the solutions of the Fokker-Planck equation, what comes out immediately is that the derivative is equal to a negative Fisher information. And if you have the log Sobolev inequality, then you obtain this very nice relationship that gives you right away an exponential decay. It turns out that under log Sobolev inequality, another inequality is coming into the game, the so-called Talagrand inequality, that put in relationship the Wasserstein distance with the relative entropy, and all of a sudden somehow you have a decay that is exponential in terms of Wasserstein distance, the distance that we introduced before. Okay, other questions, or is everything flowing so far? Very well-known stuff.
So eventually this will be true for every measure mu of the form exponential minus epsilon, under the condition that the Hessian of epsilon is positive, right? This is basically...
Yeah, not only. So it's enough that E is the sum of a strictly convex function plus an L infinity function. Okay? And so you have two components. One dominant component that is strictly convex plus a L infinity function that can make E non-convex.
Without any regularity assumption on psi?
Yeah. That's the kind of thing, except maybe that you can take the gradient of everything. So maybe C1 would be okay. Okay, so a first result that I present to you for those that may be interested. All of the things that I said are well known, very established. There is another result that we obtained that do not assume somehow this log Sobolev inequality, so we are not asking the kind of regularity or somehow the kind of shape of the non-convexity here. We are asking less. And we obtain somehow a result that tells you that the ratio between your measure rho solution of the equation and the steady state, this ratio goes to 0 with a certain rate. And the rate is not exponential. It's algebraic. It's 1 over t. And how do you prove it? Basically, you prove that the gradient of it goes to 0, but somehow, yeah, I said something not correct. The ratio goes to a constant, meaning that the gradient goes to 0, and in particular, somehow, if the measure that you have is integrable, So if the density is integrable, then the constant is the normalization constant. And if it is not integrable, then somehow your rho t converges to 0 somehow over every compact set, okay? And the assumptions on E are a bit technical, so it's kind of certain suitable growth conditions, but the analysis goes in a completely different manner. Somehow you consider the ratio, you consider of this ratio a suitable PDE that comes from the PDE of rho t, and by using that PDE, you obtain an expression of the phi with respect to any other test function with respect to this operator. And this comes with integration by parts that needs to be properly justified, because this is not the Lebesgue measure, but it is the measure that somehow it's our steady state, is a Gibbs measure. This allows you, from this inequality, to obtain a certain growth that you can use once more to estimate the behavior of the L2 norm of this phi. And altogether, by using this kind of inequality that is rearranging this one, it's possible to obtain an estimate of how the gradient tend to decrease in time in an algebraic fashion. So this is
What happens to the Gaussian heat kernel as well, right? So you will take epsilon equals 0, solutions are Gaussians, and then every time you compute a gradient, you gain like 1 over t or 1 over square root of t. Or, this is what you are saying.
Okay, this is a result that doesn't go through optimal transport, let's say. Goes another way, so it's a piece of information in the area of non-convex optimization. Now, why are we saying non-convex optimization? Because as a sigma goes to 0, what you can expect is that these, the minimizers of this functional, which is this object, tend to concentrate on a measure rho, and you hope or expect that this measure rho is concentrated on minimizers of the function E. And the function E is non-convex in general, okay? So what does it mean? It means that you can come up with the idea of considering the Langevin dynamics with a parameter sigma t that slowly goes to 0. So possibly in a way that is so slow that the Fokker-Planck equation tend to equilibrium. At the same time, you move the equilibrium, and you want to converge to basically a concentrated measure over the. This is called simulated annealing. That it's about being inspired by physics, where somehow you have a certain molecular dynamics going on, where molecules are interacting. In a higher temperature situation, the molecules are still moving around, and then you cool down the system, meaning that this sigma represents a parameter that is inverse with respect to the temperature. Okay? Sorry. This parameter is really considered the temperature of the system, and then somehow you want to see that when the temperature cools down, the system tend to rearrange the molecule in a very optimal fashion, possibly reaching a sort of minimizer of the interaction potential. Okay, the analysis of this is back to the 80s, nothing really new. I don't get into details because the idea is that on the one side, you know that this system wants to converge to the Gibbs measure, but at the same time, the Gibbs measure is moving with sigma t. And if you move the measure with a law that is pretty slow, typically you need 1 over the 1 plus the logarithm of t or something like that. you need that this is so slow that you can really catch up. And if you do so, I make it short without getting into the details, you can prove that you can minimize the function of J0, where J0 is the function of where you choose sigma equal to 0. Minimizing this means that you are converging to a measure that is fully supported on the minimizers of E. The only trouble is that this rate of convergence is a very disappointing rate of convergence. It goes like log t over log t. So you do converge, but you converge extremely slowly. Okay? It's hard to believe that numerically this really have a meaning to some extent. Okay? However, it's a very nice approach that prove with provable.
In this case, in the limit, the viscosity is vanishing.
Yeah.
And then what is the limit object you get? Because you don't have a Planck equation anymore. Right?
The limit is a probability measure
Right.
supported on the minimizer set of the function E. Of E, for me, it's the objective function. I call it E because I always think about it as an energy. Are you with me?
But what is so how do you characterize this equilibrium? Is there an equation characterizing this attractor?
No.
Before you wrote some kind of a static Fokker-Planck equation, right? You wrote
Yeah.
sigma Laplacian equal
Yeah.
to
No.
steady state.
So it's a limit of this object. So you have it, you take a limit,
And sigma goes to 0.
and you don't know exactly which limit. Okay? The only thing that you know is that the it's kind of concentrated around the minimizers of E.
Capital E. Right?
Exactly.
Yeah, but there might be multiple, right? This is like
Exactly.
classical-
And you don't know how much mass you give to different depends on the initial conditions and so on.
And then what does Shisa theorem say? That the solution converges to an atomic measure which is local?
No, it's not atomic. You start with a diffuse measure, and this diffuse measure converges to reach the infimum of the integral of E with respect to rho t. So you really get respect to rho. So that's what you get with this speed, which is...
There might be several minimizers then.
Yeah, there might be. So the limits that you get depends on the initial conditions. And they have different mass for different...
The limit of the energy, but then when you take a trajectory, yes, there is some...
Exactly. This conversion is evidently very slow, and the constant may depend on the dimension in an unfavorable manner. So we have a very nice theorem that tells you can solve non-convex optimization with a rate of convergence, okay, which is a pretty cool stuff, right? However, problem is that it's not practical for most of the problems, I believe, okay?
So, but this non-convex in the sense that it's convex plus bounded, you said, right?
It's convex plus bounded, yeah. The question is, how can you relax this further, okay? So other methods somehow that could ensure to have a more favorable rate of convergence. Second, can we deal with non-smooth problems or relaxing the assumption on E, right? So this is the question that after this point one can ask. Is everybody with me, or questions to be asked? Great. Now, long ago, before machine learning, there has been huge efforts from the practical side of algorithmic and computational mathematics or computational optimization to find methods to solve global non-convex optimization. In some cases, these algorithms are inspired by biology or by physics, as we have seen in the simulated annealing. Okay? And there is, sorry? What was the, yeah, please tell me.
No, it's engineered. Well, actually, it comes from engineering, but it's a physical phenomenon.
Okay.
But it was developed by engineers.
Simulated annealing, you mean? Okay. Yeah, but the inspiration is physical or biological, as we are going to see. Okay. So somehow this zoo of different methods fall into the somehow class that eventually has been defined like that as meta-heuristics. So they are heuristics, meaning that they admittedly do not possess necessarily proof of convergence, but in practice they are based on physical principle or biological principle, meaning that they have some justification. Okay. And this zoo came with methods like the so-called simplex heuristics, evolutionary programming, metropolis hastings, simulated annealing, we talked about it, genetic algorithms, particle swarm optimization, ant colony optimization. So it goes like that. Okay, ant colony, you feel that already is biological. There is a group of ants moving around, leaving a chemical information to attract the others, and so on. And the idea was to use all of these analogies to design algorithms. For the moment, I will speak about particle swarm optimization. Maybe later I will go back to maybe genetic algorithms if I have time. But let's talk about particle swarm optimization. What is in common with these methods is that despite empirical success in certain benchmark for some of these methods, they still lack a little bit of theory somehow. That's the common method. Let me talk about particle swarm optimization. Here, somehow, again, probably produced by practitioners, maybe engineers or computer scientists, but with an analogy to physics. In this case, it's a Newtonian dynamics, meaning a second order. We have a velocity, we have an acceleration. And in this equation, there are forces that somehow pull a certain number of particles, here we have n particles, towards a first point that they call yk. And the point yk for the particle I represent the location where the particles has sensed the best value of the function E. Instead, here we have another force that pull the particle towards the best of the best locations. So it's a sort of collective best. So we have a first, which I call personal best. In the history, the particle have seen points, and if the next point is better than the others, then this is the new best point. Otherwise, it keeps trying to return to the position where it was. At the same time, you try to create a sort of global best, a sort of communication between particles. At the same time, you want to explore, meaning that these matrices appearing there are random. Okay? Now, this discrete time dynamics, it's hard to analyze.
Sorry, which are random there?
R are diagonal matrices, okay, of diagonal entries that are basically randomly taken. Okay? This is how this was proposed, and it became extremely popular. So if somebody in industry want to solve a non-convex problem, the first thing that they take is this method and they try it. Okay? There is no justification why this method works. There are some little attempts of proving it to converge locally, let's say. And what...
But you have to refresh the matrices in every step, R1 and R2?
Sometimes they do a refreshing of the matrices.
You can keep them also fixed?
No, they generate it at random at every iteration. In order to be able to analyze this stuff, and we will understand how this come later, because it's a kind of very nice universe that keeps together, but we have to understand piece by piece. There's been an attempt done by Paresky and collaborators to rephrase the particle swarm optimization as a discrete time description of a stochastic ODE system where you have these drifts towards the personal best and the global best, and then certain diagonal matrices that depend on the coordinates of the vector connecting the particles to the personal and global best, perturbed by Brownian motion. That's what they do, and they try to connect the two with a proper somehow choice of lambda 1, lambda 2, and sigma 1 and sigma 2 with respect to the coefficients that appear here. Moreover, they wrote a ODE that is a relaxation of the update of this type. Okay, so basically, if the current version, the current point is a better location, then you try to move in that direction, and creating a very fast drift towards that, and you couple the two things. Okay, that's a way to try to represent this. However, still the system is pretty complicated. Okay, as you can see, it's a stochastic differential equation coupled with SDE. So the question is, how can we make it even simpler to be analyzed? Okay, and here comes the first simplification, which is the so-called zero inertia limit. So you introduce some mass in the particles, compensated with a little bit of friction that comes here. And the friction is getting stronger and stronger as the mass goes to zero. By doing so, if you take formally the limit for the mass going to zero, it turns out that you can describe here this term explicitly as a somehow an equation with respect to this right-hand side that you can see. So if you bring the VI on the other side, you have an expression for the velocity. If you have an expression for the velocity, you can plug it in the first, and all of a sudden, from a second-order dynamics, you fall into a first-order dynamics. So this is a sort of overdamped somehow representation. Okay, we simplified a little bit this Newtonian dynamics, and then comes, yeah.
The laws of the X are still Gaussian.
I'm sorry?
The laws of the XT are still Gaussian or non-Gaussian?
The laws of this, no, they are not in generally Gaussians, no.
But can you say something about it?
Of the XTs, we will get to that. Of course, these are Brownian motions. BT, they are Brownian motions. Yeah, we will see what happens. And now comes into the game a very important paper that comes with a very good intuition by Pinot, Totzek, Tse, and Martin that open up a field, I would say, in 2017, in which I started to operate afterwards. And they proposed the following. First of all, the zero inertia limit. Okay? The second is, let's forget the personal best. So let's forget this part of the equation. So the first drift, let's forget it. The second was to substitute the global best with an approximation. So we approximate the global best with the center of mass of the current distribution of the particles weighted by the Gibbs measure. So the particle that has the minimal value gets a lot of mass, while the particle with less value doesn't contribute too much. So this is a weighted center of mass, weighted by the, okay? And it is a proxy for the global best, actual global best. You with me? Questions? Over there, I see always a little bit of doubts. Clear? Wonderful. If you do so, all of a sudden, you can collapse everything where you substitute the global best with this point that in the literature of this kind of dynamics is called the consensus point. So the particles somehow produces a first consensus proxy for the global minimizer. They are drift towards this consensus point. At the same time, as long as they do not agree, and they are far apart from the consensus point, they continue to explore. Are you with me? Okay, questions. So this equation is made of two parts. One deterministic, where you exploit information, and another stochastic, where you explore. And you let exploration vanish as long as the particles are uncertain. Okay, this is the modeling. In a certain sense, this diffusion vanishes as it were in the simulated annealing. So to some extent, these simple dynamics carry the ideas of particle-swarm optimization. At the same time, it carries also the ideas of simulated annealing. It's a fusion, but very simple. The other difference is here that no gradient of the energy comes into the game. The only thing that you look at is the value of the energy. So you are evaluating a zero-order information. So in principle, E can be non-smooth. As long as you can evaluate it, you can deal with this thing. You can discretize in time, you can run it, you don't need the gradient. The only thing that you have to pay is that you do not have one algorithm, but you have n algorithms that they are talking to each other. Okay? Is it a price that you're willing to pay? If I talk to my collaborators in the engineering, nowadays, as long as you know how to parallelize this, they say, yes, absolutely. This can be done. It's great. For us, it's fantastic. I will get to that later. Okay? So, yes, you have n times the cost of what you can do with stochastic gradient descent, but you can deal with non-smooth problems. And on top of that, I do promise to you that you converge to global minimizers with a decent rate.
What is the role of capital N there? You can take any N, but...
We will get to that.
But probably the energy function should be at least continuous.
Yeah, you need to be able to evaluate it. Of course, if you want well-posedness and all this stuff, you need a little bit more than that. Okay? So, but if you want well-posedness and doing the analysis, you need a little bit of smoothness, a little bit of growth, and so on. But if you want to implement, you don't need anything more. Now, the zero inertial limit has been proven very nicely. So there are some papers that really make everything rigorous, okay?
Zero inertial limit means that you take first order for x and you pass to the limit as t goes to
No, the zero inertial limit means that you pass from the second order to first order.
But then they do it probably on finite time intervals.
In this paper, I believe so. Yeah, global, difficult. Oh, no, that's very bad. Okay. Now, to show you in an exaggerated simulation, meaning that I'm using too many particles. For this, you need 5 particles, not more, okay? But I'm exaggerating to clearly show you how it works. Okay, this speaks more than words. Okay?
So in blue, this is the landscape of the functional?
Yeah. Yeah.
So there might be many local minima in particular.
Yeah, you can have no growth, many zillions of minima in the middle, you don't care. Okay? Of course, this doesn't mean that you don't solve problems in dimension 1000. You solve problems in dimension 1000. Okay? So here you can see a function that has multiple minimizers. This is called a Rastaging function. It's affected by the curse of dimensionality, meaning that the number of local minimizers grows exponentially with the dimension, and we are able to solve this problem in very, very large dimension. Okay? You with me? Okay, great. Now, discretization, for the first idea, we can certainly use a simple Euler-Maruyama discretization. One can use more sophisticated method. I don't know whether I will have time to say anything about it. But as we see, somehow, when the number of particles goes to infinity, what you want to expect is that each particle start to behave as an instance of the solution of what we call a monoparticle dynamics that is self-consistent, meaning that here you have the empirical measure, and here you get a non-empirical measure which correspond to the law of the particles. And now I come back to the question over there. This law is not Gaussian in general. Okay? It's not Gaussian. As we have done before, it solves a partial differential equation. You remember that we derived from the SDE a PDE, and the corresponding PDE is of this type, that is on the one side non-linear and non-local, at the same time with vanishing diffusion, okay? Which makes it intriguing. And it is not corresponding to a gradient flow of anything, because we are destroying here a sort of entropy that comes into the game. You with me? And so you have to have an ad hoc analysis to understand what is going on when the t goes to infinity. Are you with me?
So if I forget all the rest and I just focus on this
PDE,
Fokker-Planck-like, so this is rho is a density, and then I have the diffusion sigma is vanishing as t goes to infinity, right?
no, sigma remains.
Sigma is fixed now.
What is vanishing is the fact that this is going to a delta. And going to a delta, you get 0 here.
Who is going to a delta?
Rho t will converge to a delta
Delta on a single point? Or
on a single point that is a global minimizer.
which is not assumed to, the global minimizer is unique?
So we can both. It can be unique, it can be non-unique. We have a theory that explains both.
But when the global minimizer is not unique,
You converge to 1.
cannot be half and half? Cannot be an average of
No.
two deltas?
No. No, you converge to 1.
Depends on the starting point.
It depends on the starting the distribution where you go.
And X alpha is this average you have described before?
Yeah. X alpha is the proxy to the global minimizer.
This X alpha.
Yeah. And we have versions of this equation or this dynamics that are modified to converge to distribution on the set of minimizers. So in such a way that you don't collapse to a delta, okay? But we have some other models of this kind that are not designed to converge to one point.
And is there a PV proof of this as the one you have mentioned before? I don't know, using...
Yeah, I show you.
Okay.
Yeah. Okay, now I just tell you that the convergence of this system, okay, to this is what we call a mean field limit, or more precisely, when you can quantify how it goes with the number of particles, it's a quantitative mean field limit. That's what we call it. And you can prove that this quantitative mean field limit goes like n to the minus 1/2. Okay, so if you take this 2 and you plug it there, you can explain how the empirical measures will behave as instances of the monoparticle dynamics with a rate that is quantitative. Are you with me? By now there are finite time quantitative estimate, but also uniform in time quantitative estimate. Okay, there are some additional work done in this way. And so we can explain how this converges to this. And now the question is, what happens to for the large time behavior? I avoid this analysis. I give you an intuition, though, which is pretty cool. Now, you take multiple particles, and 3 particles, you let them start from always the same 3 points. The other particles are randomly chosen and they start from other points. For each of these experiments, you track the trajectories that 3 particles did starting from these 3 points, and you record them and you create clouds of these trajectories. You with me? And then you take the average of the trajectories that the particles did in the multiple experiments. And the very surprising thing is that the average particle is a straight line from the particle, initial particle, to the minimizer, global minimizer, regardless of all the local minimizers that are around. So what you are actually doing is minimizing. You go the gradient of the quadratic distance from the global minimizer. So to some extent, the consensus-based optimization for the number of particles going to infinity is a canonical convexification of the problem to a quadratic problem.
Well, but convexification is convexification, not always is quadratic, right?
In this case, you start from any non-convex function you want, you end up with a quadratic function. So the behavior for the number of particles going to infinity is to eventually, okay, minimize the quadratic distance on average from the global minimizer. So this is the phenomenon that you can observe in the experiments. How to make it concrete? So if your function grows a little bit around the global minimizer, the global minimizer is included in the support of the initial distribution. And then we will remove this assumption. Okay? And it is locally Lipschitz, so very small assumptions. Then the Wasserstein distance of rho t from a delta on the global minimizer decrease exponentially fast with a rate that depends on the drift parameter and the diffusion parameter. So if the drift is sufficiently strong with respect to the diffusion, then you converge in exponentially fast up to a certain time t star, okay, that allows you to reach an epsilon accuracy. For that, you need to take alpha, which is the inverse temperature parameter in the way you compute the consensus point, sufficiently large. Okay? So for every epsilon, there exists an alpha sufficiently large and a time that is sufficiently large such that this is exponentially decreasing up to that point. Okay? On top of that, by using the quantitative mean field limit and some numerical analysis of stochastic differential equation, you can prove that the algorithm converge to the global minimizer up to a certain tolerance with a probability that approximate 1 with a rate that is quantitative. Depends on the number of particles, depends on the discretization time, and depends on the number of iterations. Okay? So how do you prove that? So you take the Wasserstein distance squared and you differentiate it along the solution of the PDE. Now, I call the Wasserstein distance this curly V, okay? And then I differentiate it along solutions of the PDE. What comes out is already very nice. You have here a relationship that indicates exponential decay. However, I have other terms that are related to the, oh, here a minus is missing. Okay, here a minus is missing, but they are related to the distance of the consensus point from the global minimizer. Are you with me? So if you could estimate this as the square root of the curly V times a constant, then you could absorb that into this term. And the interesting fact is that for alpha going to plus infinity and uniformly in time, in a finite time, you can indeed prove that this can be made as small as this for the amount of time that you need. So basically, what you try to prove is that somehow this term is less or equal than a certain constant times square root of V rho t for a suitable amount of time as long as alpha is large enough. This is a very technical part of the proof, okay? But if you work out this, then you can absorb these terms within here, obtaining a minus t or minus tau, and then you have an exponential decay. Okay? That's the technical part of the proof. Proving that somehow this consensus point is close to the global minimizer is what we call a quantitative Laplace principle. Okay? So this comes with certain inequalities that relate this distance with the Wasserstein distance, or the square root of the Wasserstein distance. Okay? Okay, so eventually you get a convergence in probability with a certain rate that depends on the number of particles. This constant may be terrible. Why? Because if it's true that we can convexify any problem, then we would have proven something amazing, that you can solve every problem without difficulty, even in high dimension. But if this constant goes like an exponential in D, then you need an exponential number of particles with respect to the dimension, which is happening. So for some problems, I mean, you cannot circumvent the fundamental issue that no algorithm could ever prove being able to solve that problem with a number of evaluations of the function that is not exponential in time. So we cannot do magic, okay? Certain problems remain difficult, and this cannot solve the problem. I mean, I'm not selling that you solve everything with n to the minus 1 and so on. That's not what we are in this message. However, for many, many problems that we are facing, this is a good algorithm. And we do have also some theory that support it. Okay? Back to one point. The assumption that the minimal point here is a V star, but it should be X star. Sorry, it's a typo. That X star is in the support of the initial distribution has been removed recently. So this equation is a diffusion equation. Okay? So even if you start with a compactly supported distribution, at a time t larger than 0, this diffuses everywhere. However, due to the fact that there is this non-standard diffusion, made it not obvious from the beginning that you are really diffusing nicely. So you have this term that you don't know whether diffuse very nicely, okay? But that's what we have been fixing recently. So we have a paper that shows that indeed, at a time t larger than 0, whatever rho 0 you take, the density becomes positive except on the consensus point. So basically, you can prove that you have non-zero mass around the consensus point. Okay, so sorry for the typos because I copied things in the meanwhile. Okay. There are tons of variations on the theme. Now the topic has exploded, meaning that there are a lot of papers on this. There's a lot of things going on. You can have different noise. Instead of having isotropic noise, you can have anisotropic noise. You can have, if you want to have gradients in the story, you can put gradients. If you want to have memory, so considering this idea of having the personal best, this can be done, and it has been also analyzed. And you find some of these things into these two papers. If you, it's non-Markovian. In this case, it's non-Markovian, yeah. 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 And so here there are some other analysis that has been done. Okay. Well, yeah. Well, you make it Markovian here with the trick, but yeah. Okay. So on the left, we have the consensus-based optimization. On the right, we have the second-order dynamics, which is the particle-swarm optimization. You remember, we started from the particle-swarm optimization. And it was a Newtonian dynamics. You with me? Great. So this is what Newtonian dynamics does, right? And that's what consensus-based optimization does. So you see that the dynamics is pretty different. And in practice, consensus-based optimization can outperform particle-swarm optimization. Okay. In the meanwhile, though, there has been attempts of bringing the mathematical ideas to the analysis of particle-swarm optimization, and there is some proofs of local convergence now of particle-swarm optimization based on these ideas, okay? Okay. I like to report this important collaboration I have. Now, some of you have seen robots doing whatever you want. Dancing, acrobatics, all that stuff, right? Well, the truth is that all those dynamics are prescribed. Nothing is computed on the spot. So even letting a robot walking and computing how to walk, so from a certain standing position to another standing position, and say, I want to optimize the movement from here to there, okay, making 2 meters, so learning to do a couple of steps, and computing on the spot what to do, it's a difficult non-convex optimization problem. If you use state-of-the-art methods like covariance matrix adaptation, evolutionary strategies, so CMAES, or what has been used in the past years by the robotics community, which is called MPPI, meaning, what's the MPPI stands for Model Predictive Path Integral, okay? They are not able to make the robot walking. By using a relatively vanilla implementation of consensus-based optimization, it seems that we have been able to make the robot walking. Okay? This is a very, very recent result, published in one of the most important conferences in robotics in this year. And it seems that in this area, you cannot use gradient descent. You cannot use stochastic gradient descent. It doesn't work. It doesn't reach global minimizers. Moreover, in some of these cases, you have contact type of relationship, so the dynamics is usually non-smooth, and they are really interested to have zero-order optimizers. And they do not care how much does it cost, because if you have a good parallelizer, they are happy to parallelize, okay? And so this seems to work really great. Now let's dare even more. Let's consider a difficult problem, like minimize the Ginzburg-Landau energy. The Ginzburg-Landau energy is minimizing the double well potential. So the function wants to take either the W1 value or the W2 value. And if transition between them, it does want to transition in such a way that has zero gradient as much as possible. If you start with initial conditions that are not W1 or W2, you are forced to transition, and you have zillions of local minimizers. Okay? Any transition between these two values become a sort of local minimizers. Computing global minimizers of this non-convex energy is a difficult problem, because you have so many, you have continua of local minimizers. Okay? Here you can see that we can compute global minimizers with obstacles for different parameters P and different parameters epsilon. Okay? 10 lines of code. Okay? So, and this is in principle an infinite dimensional problem that you discretize on a grid, become a non-convex optimization problem in Euclidean space, and you can do many, many things. You can solve problems, it's so versatile the entire business that you can solve problems on non-convex problems on manifolds with variable curvature, okay? So you can do a lot of other stuff. Of course, you can solve problems on homogeneous spaces like the sphere. And yeah, then, I mean, of course, you can expect more and more applications. Okay, I think that, you know, unless there are questions that are interesting for unless you have more questions, maybe I would not overload with further information. So what I'm saying is that now we have constraint optimizations with, we have seen this with obstacles. We have different type of noise that you can inject. You can use multi-objective optimization, solve the point problems, solving for several minimizers simultaneously, using it for sampling. You can use memory. You can inject momentum. You can inject gradient. The particle swarm optimization has now some proof of convergence. In this paper that you can find on the archive, we just connected consensus-based optimization to evolution strategies, so CMA-ES, and we proved how evolution strategies are globally convergent under a suitable framework. So the technology of consensus-based optimization do allow us now to prove also things there. And the final considerations, CBO convexify any non-convex problem. It does work, it's all-purpose, derivative-free. It can be combined with classical methods, it's parallelizable. You can include other important effects. Can be used for geometrical optimizations on manifolds. It can explain other methods like particle swarm optimization or evolution strategies. And here you can find a little bit of literature. Mainly my own literature from my group. It's a curated literature. By now there are hundreds of papers on consensus-based optimization. And for those that want to somehow use software, there is a sort of community effort now to create more and more efficient software for consensus-based optimization. And with that, I do thank you.
Thank you, Massimo, for this very interesting talk. I think we have time for questions. There seems to be no one coming, so.
Thanks. Thanks a lot for the talk again. I had actually a couple of questions, but the first one is just a clarification. Back in the equation where you said that we had the diffusivity going to 0, right? The transport term is also going to 0, right? Or not? Okay. But this doesn't create any kind of issue or maybe you can ask also the second question since you're here, so then you can answer to both of them. The second was about the experiment in robotics, right? And I know that in robotics, when people need to optimize the movement of a robot, there's a big issue, which is the one that there are some moves which are unfeasible. So the state space is constrained, right? And I wanted to ask if this can be easily implemented in consensus-based or not. Ah, okay, yeah, thanks.
Right, so the first question is that the drift has to be stronger than the diffusion, as you see also from the math. So lambda, okay, has to be larger than sigma squared. And the reason is that on the one side, you want to collapse to a delta. On the other side, if you lose control, this can become larger and larger, so the variance can continue to explode. So if you don't have this control, so if lambda is not larger somehow of the 2 lambda larger than d sigma squared, then unfortunately you don't control the exploration.
And what is this assumption? So you are assuming lambda greater than sigma squared over 2? Or?
Yeah, because in the decay, you get that. Otherwise, you lose control.
You can see it already, I think, from the basic Langevin context.
Yeah, maybe.
You have a constant diffusion term.
Yeah, but here you don't have.
Yeah, no, it's the same phenomenon.
Okay, the other question is, yes, of course. I mean, this is an example, right? So you can easily implement obstacles.
Yeah, thanks for the talk. You mentioned that this is easily parallelizable, but I imagine that you can also do some sort of randomization strategies or batching strategies in the number of particles in order to fasten the algorithm. Is there a preferred or canonical way or theory-based way of doing this? Or I'm interested in this. Thanks.
So the right way to parallelize this is current work in progress. So I'm not disclosing exactly how to do that. What I can tell you is that you want to minimize the number of communications. So you don't want particles to communicate with all the particles. Okay? First of all, you want to create local information that is exchanged by particles. At the same time, you have to correct the guess on the consensus point. How to do that correctly, it's the key of a paper that we're finishing, so I'm not entering in that detail. Concerning batching, yes, there is some work done by some colleagues from Korea and of the group of Seung Il Ha, with collaborators with Shijin, and they worked on somehow sub-batching, let's say, some sapling particles to make it faster. But I did not get into the details. So we are currently working in the way you create the clusters of particles that can, in a certain sense, exchange information. But it's a core of a paper that we are finishing, so just to be fair with collaborators.
Yes. I can speak like this. Okay, just maybe in case there is someone online, there might be. So how do you, in principle, deal with manifolds, with optimization of manifolds? Because your methods might be not thin enough to be on manifolds. I mean, there would be several ways, but please tell me.
There are multiple ways. One way is if your manifold is a compact, let's consider a compact surface. If you compute the consensus point, it will be outside. It falls into the convex hull of the particles. Are you with me? One way to do that is to project onto the tangent space the direction pointing to this off manifold consensus point, and do some corrections on the Brownian motion to avoid the Brownian motion, the Ito corrections, that in a way that also the Brownian motion is tangent. Surprisingly, the fact that you do not compute a consensus point directly on the manifold, you don't compute a true barycenter, a Riemannian barycenter, but you do it in Euclidean embedding, does work anyway. That's the first answer. Apparently, with compact surfaces, it works very well. Another way is by using penalization, meaning that you are penalizing the fact that you are not on the manifold. This has been used by other people, especially if you describe, there is a work by José Antonio Carrillo and collaborators, where they describe the manifold as the solution set of a certain equation. And then they are penalizing the equation, and you can do that. It works very well in practice. José Antonio Carrillo. Carrillo, double R and double L. There is some work done by a master student of mine that is trying to use to work on homogeneous spaces or Lie groups like SOD. And he's trying to develop a theory that is intrinsic on the manifold. I don't know exactly whether I will have the chance to hire him as a PhD, but this could be some further work to be done. But there are multiple approaches, either projection approaches, as we do, or penalization approaches. They do work.
Any other question or comment? Yes.
Thank you for your presentation. So maybe a simple question, but about the property that the average path goes towards the optimal point. Doesn't it, about the property that you mentioned that the average path is straight towards the optimal point, doesn't it give you a species of acceleration method if you point, you start from two different points, they are pointing to the same place? Is it possible to be done, or does it make sense? I mean, you have different straight lines pointing towards the same direction, then by starting from different points, or basically looking to the same optimal point. Yes.
My answer is that, first of all, what you see here, it's the average behavior. Otherwise, the trajectory may point in the wrong direction. So here there is some trajectory that may point here, this trajectory point there. Is the average trajectory that points right? First point. So in general, the information of the trajectories, the velocities, let's say, it's wrong. It's becoming right in the limit for t going to plus infinity, or for the number of particles going to infinity, but in general, it's not right. Second, in high dimension, you have so many directions that somehow even n particles cannot really predict. Nevertheless, the consensus point itself, it's already an information, a global information of belief where the global minimizer may be. Yes, you can inject maybe also this geometrical information in the story. I don't know how reliable it can be in very high dimension, okay? Given the stochasticity and given the fact that in very high dimension you have so many possibilities of geometrical.
Other questions or comments? No? Okay, if not, we thank again Massimo.